So this limit, what you'll notice is x is approaching infinity. And that's what makes this limit new from the previous limits that we talked about, right? Okay. What I'd like to do is take advantage of the following idea. Just for a side note, think about this limit for a minute. The limit as x goes to infinity of, say, 117 over x. And this limit, if you understand this limit, then this one up here above will be easy once we rewrite it. Well, just think about for a moment. If x is going to infinity, like this says, what that means is x is becoming a bigger and bigger and bigger number. So 1 million, 2 million, 5 million, the biggest numbers you can imagine. If I take 117 and I keep dividing it by bigger and bigger numbers, the answer I get gets closer and closer to 0. So the answer to this limit is 0. So I know I could take a fraction and multiply it by 1. I just got to multiply it by a clever form of 1. So that's what we're going to do. If you look at that thing in red, that definitely equals 1 because it's the same thing divided by itself. So it doesn't change the value of anything. But when I multiply this, watch what happens. I get 117 over x squared minus 1. And then in the denominator, I get 3 plus 12 over x plus 36 over x squared. Don't forget, when you multiply this, you're going to multiply it by both things on the top. This one gets multiplied by all 3 terms on the bottom. So some nice canceling happens. And now we're still asking for the limit as x goes to infinity. Well, if we just think about this idea, we can apply that here. The terms, like this guy here, is going to become 0. This will become 0. And this will become 0. So there you go. So what are you left with? Well, you get negative 3 over 1, or negative 1/3. Right? So that's the answer to your limit. Now, it'd be nice to take a look at what this means graphically. Okay, so what does this mean for our picture? We've seen other things about limits in the past, but what does it mean? So what we're going to do is we're going to take this function and we're going to put it into the calculator. Okay, so here we go. I'm going to go to y equals. I'm going to get rid of whatever plot is there. Okay, and here we go. So open parenthesis, 117 minus x squared, close parenthesis. Oh, I got 2 minuses there. Hold on a second. This thing is so slow sometimes. Delete. Oh, great. Okay. So here we go. 117 minus x squared, close, divided by open. And let's remind ourselves what it was. 3x squared plus 12x plus 36. So 3x squared plus 12x plus 36. Hit enter. And there we go. So now what I'm going to do is I'm going to get a picture of this graph. So here we go. I'm going to go to zoom 6 to get started. And we'll see this picture. It does some fun stuff. But what you'll notice is, or if you think about it, we're really only interested in what happens when x gets really big. So for example, I'm interested in, if x is going to infinity, that means I'm looking over here and I'm saying, hey, if x gets large, I'm heading out in this direction. What does the graph seem to do? Now it looks like it's leveling off, right? But we're only at x equals 10. So we need to go a little bit further to start seeing what happens. Now we have 2 options here. One thing we do is we can go to Window, and we go to X max here, and we can make it bigger. So maybe I can make it 100. Now that's not really far along the x-axis, but it's a little bit further. And I can press Graph now and take a look at it. And what I start to notice is that graph now dips a little bit below the x-axis. I can kind of see that here. It comes down, and it seems to be slightly below the x-axis. Let's think about what the limit was. The limit as x went to infinity of this function was equal to negative 1/3. So maybe I'm not surprised that this thing is dipping below the x-axis. But here's another way to look at it. You go back to your calculator, you can go second graph and go to table. Okay? And what you'll notice is this. We have x values on the left and y values on the right. All right? And we can change things a little bit. So let's make the delta table 1 and hit enter there. And what you'll notice is, look at those y values as x gets bigger. So as x is getting bigger, we got 7, 8, 9, 10. it starts to turn into something negative, and we don't really see it yet for a while, but if I hold this down and I wait, you can watch those y values on the bottom. They look like they're becoming more and more negative. It would be nice to see something further along. So if you go to second table, I'm going to change, second table setup, sorry, that. I'm going to change table start to 100. And then I'm going to do delta tables by 10. And now watch what happens. So if I look at that table now, what you notice about those y values are they're getting really close to negative 1/3. That's what's starting to happen. Visually, what this looks like, or should look like on the graph, is this. The graph does whatever it does over here. It had the drop gone up and down and so forth. But when we get really far out to the right, what we should start to notice is the graph levels off at a y value equal to negative 1/3. So it's getting very, very close as x goes towards infinity. So that's called a horizontal asymptote. There's something about this problem when we look at it at the beginning that makes it nice to solve. And if you look at it, what you'll notice is when we multiply by 1 over x squared, the thing we get below ends up with two terms that don't go to 0, right? But the rest all do. So that made things really nice. So let's ask about a new limit. What about the limit as x goes to infinity of, let's say, 7x squared plus 20x plus 100, or 1,000, whatever. And then on the bottom, let's pretend we have this, x cubed plus 3x squared minus 117, my favorite number. So we're going to multiply by 1 again, but this time we're going to multiply by 1 over x cubed. And you might say, why that? Well, because it's the highest power of x I see in the problem. And watch what happens when I multiply through by that now. I've got to distribute this onto every term. So this becomes 7 over x plus 20 over x squared plus 1,000 over x cubed divided by, and now here comes the fun part, 1 plus 3 over x minus 117 over x cubed. And now I can say, hey, what's the limit as x goes to infinity? Right? Well, if x goes to infinity now, this becomes 0, 0, 0, 0, and 0. So in reality, all I'm left with is 0 on top and 1 on the bottom, or 0. So this graph also has a horizontal asymptote of y equals 0. So it's getting closer and closer to the x-axis as x gets really, really large. So you may or may not like this idea of multiplying by this form of 1 we're picking, but there is another way to do problems like this. So when you're faced with a problem as limit as x goes to infinity, and maybe you have some polynomial on top, 177x cubed plus 15x, and then on the bottom you might have 150x minus 200x cubed, and you have to find this limit, that you can find something called an EBM. I'm not going to write this out, but this stands for end behavior model. And what an end behavior model does is, or what it does is it helps you get the answer to this limit a little bit more quickly. To find an end behavior model, you take the highest power of x on top, which in this case is an x to the third. And then you divide that by the highest power term of x on the bottom, which is negative 200 x cubed. So what we're really saying is when x gets really big, x cubed is more powerful than x. It's going to dominate x. And you can think about that. If you plugged in 100 cubed is way bigger than 15 times 100. So this term is going to win out in the long run, just like this term on the bottom is going to win out in the long run. So these are your two most powerful terms. So end behavior model says just divide your two most powerful terms and see what you get. So in this case, you'll get 177 over negative 200, but that's the answer to this limit. That's all you have to do. So let's consider some other possibilities. Let's just take this limit I gave you and change it ever so slightly. So let's say limit as x goes to infinity of 117x to the fourth plus 15x over 150x minus 200x cubed. So again, to find the EBM, you do this the same way. You start off, and behavior model is going to be the highest power term on top, which is 117x to the fourth, divided by the highest power term on the bottom, which is negative 200x cubed. Now, a little bit different this time, right? Because when you reduce it, you get 117x over negative 200. Well, that's not a number, right? I can't give that as an answer to a limit. I have to think now about what happens if x goes to infinity. So you have to do a little bit of work here, but not much. Just ask yourself what happens if I take a really huge number, multiply it by 117. I'm going to get a really big number. And then when I divide it by negative 200, I get a number that's very negative. So the answer to this limit is negative infinity. So this is an interesting application, or I should say implication, graphically. What it means is that as we move really far out on the x-axis, as we get over here where x is heading towards infinity, the y values, remember this answer to a limit is always the y value is going down really far. So this graph has no horizontal asymptote, no HA. Okay? Whereas the graph up above, if we had thought about what this graph probably looks like, what that means is x goes to infinity. If I go really far to the right, the y values I'm getting are getting closer and closer to that fraction, whatever that is. Okay, it's a little bigger than negative 1. So there's a dotted line here. It's y equals negative 177 over 200. And the graph is leveling off there somehow as we go really far to the right. Okay, let's consider one last tweak of this limit. Let's take the limit. Say the limit is x goes to infinity of 117x squared. What was it on the top? Plus 15x. And on the bottom, we have 150x. Hold on a second. 150x minus 200x cubed. So if we do an EBM in this case, look what we get. We get 117x squared over negative 200x cubed. And when we reduce it, we get 117 over negative 200x. So again, you have an expression that has x in it. So you can't just give that as an answer. You need to ask yourself, what happens if x gets really big? What happens if I put a huge number and put it in this expression? What do I get back? This thing gets close to 0, and that's the answer to this limit. Graphically, what does this mean? It means that as we go really far to the right, this graph is leveling off near the x-axis. So this graph also has a horizontal asymptote. So in terms of what to expect, if your higher power term is on the bottom, you should expect x or y equals 0 to be your horizontal asymptote. If your highest power term on the top and bottom match, in other words, if they both have the same highest exponent, you can expect the coefficients to be your horizontal asymptote. And then lastly, if you have a higher power term on the top, then you can expect an answer of positive or negative infinity, but you won't get a horizontal asymptote.